In this optimization problem, we have a situation where we have a boat on an ocean that's 6 miles from the nearest point on a straight shoreline. And that point is 17 miles from a restaurant on the shore. Woman plans to row the boat straight to a point on the shore and then walk along the shore to the restaurant. If she walks 3 miles per hour and rows 2 miles per hour, at which point on the shore should she land to minimize the total travel time, and what would be her minimum time? So she could go straight across and then walk the whole thing, but that's going to be the farthest distance. The shortest distance is going to be just rowing straight across. However, you row slower than you walk. So there's some sort of a combination that she's going to want to do, right? So take some sort of an angle and then walk the rest is going to be her best option. So we're trying to figure out how to minimize her time, right? That's our goal. Minimize time. All right, so that means we need some sort of a time equation. So we got to figure out how to make this happen. So what we're looking for is she's going to be shooting for some distance down the shore, right? And so that's distance down the shore, we don't know. That's what our goal is. And then she'll walk the rest, which is 17 minus the x. Okay, so she's shooting for some point down the shore, and then she'll walk the rest. So we have a time kind of a thing. We need time equations, time relationships. So what we have going on is a rate times time equals distance kind of situation, but we need to focus on time, not distance. So distance plays a role, of course, because the rate, time, and the distance all play a role. So our time equation is going to be a distance divided by time. No, sorry. Distance divided by rate. So distance divided by rate. So if we isolate the time, we're going to divide. So we need on our time, it's going to be related to this distance down the shore that we're walking or that we're aiming for, is we need this distance and we need this distance, right? So this distance, we're going to then divide it by a rate. So we're going to take this, whatever this is, and we're going to divide it by a rate at which she rows, which is going to be dividing it by 2. All right, and then, so that's going to be a time. So that's going to be a distance divided by her time. And then we're going to take another equation because that's part of time. And then our other time is going to be this distance divided by the rate at which, because it's distance divided by rate, the rate at which she can walk. So this is the piece that we need to figure out. What is this distance? Well, that distance is part of a right triangle. That we know that's 6, we know that's x. And so if you do Pythagorean theorem on this, you would do 6 squared plus x squared, and then you would square root it. So that distance is going to be x squared plus the 36, and then you'd square root it. So that's that distance. So x squared plus 36. All right, so this is what we need to do the derivative of so that we can maximize or minimize. And we're trying to minimize. So we need to kind of rewrite it a little bit in order to kind of get it ready to do our derivative. So I don't like the way it is. So let's rewrite this. This is a 1/2 multiplied to this square root that I'm going to rewrite as a 1/2 power. So it's ready to do the derivative. And then this fraction, I'm going to break it up into 2 fractions, plus 17 thirds minus 1/3 x. So then that's a little nicer and easier to do the derivative of. All right, so we're ready to go. So let's do our derivative. And we're going to have a 1/2 times a 1/2, which is a 4th. So this is a chain rule. And then raised to a negative 1/2 times the derivative of the inside. So we just did the derivative of the outside times the derivative of the inside is a 2x. Derivative of 17 thirds is going to go away. And then the derivative of negative 1/3 x is going to be a negative 1/3. All right, so we're going to take that and set it equal to 0. So I'm going to clean it up as I set it equal to 0, and let's do the math on it. So this is a negative 1/2 power, which means it's a square root that's going to go in the denominator. This 2 can simplify with this 4. And so I have an x on the top over a 2 times the square root of x squared plus 36. And then minus 1/3. And that is going to be set equal to 0. All right, so if I'm going to go ahead and try to solve this, I'm going to actually try to do it by hand. So I'm going to bring the 1/3 over. So I have x over 2 times the square root of x squared plus 36 equals 1/3. And then if I squeeze that in here, if I cross multiply to solve this, I'm looking at a 3x equaling a 2 times the square root of x squared plus 36. And then if I try to cancel out my square root, I'm going to square both sides. So if I square this, I'm looking at a 9x squared. If I square this, I'm looking at a 4 times x squared plus 36. So that's a 9x equals 4x squared plus 24, 144. All right, and then I'm going to try and solve that. All right, so to solve that, I dropped my square. All right, so if I keep on solving this, that actually made it much nicer. So I'll subtract the 4x squared over, so I'm looking at a 5x squared equaling 144. Divide by 5 and square root it. I get x squared equals, don't square root it yet. Square root it. So we're going to divide by 5 and then square root it. So if I square root that, I'm looking at a 12 plus or minus a 12 over the square root of 5. And my negative is not going to make sense for my answer because we're talking about a distance. So we are just going to focus on the positive. And so we're looking at, just to kind of make some sense out of it, that if we rationalize it, we have a 12 square root 5 over 5, which is approximately 12 square root 5 divided by 5 is approximately 5.367. So that is 5.367 miles down the beach is what your aiming point is. And we'll walk the rest. So how much time does it take? So, because we're looking to answer what would be her minimum time and at what point on the shore. So she's looking for that point down the shore. Her time is, let me do a couple of them. We're going to go, remember, we have this time equation and it's all based on what distance down the shore we're going. And so if I plug in this 5.367, if I were to take this value and plug it into this equation, it would be roughly 7.903 hours. Right, so almost 8 hours. And then let me throw a couple more situations just to show you that the other two scenarios that we kind of think of would definitely not be the best. So if she didn't do any distance and she went just straight down, no distance, we made this a 0. She went here at 6 and then here at 17. If you were to make that a 0, then that, if you plug it in, would be 8.667 hours, right? So definitely longer. And then if she went straight across and just rode, so if she went straight across and just rode, we're looking at a distance of, I don't know, we would do the square root of, because we would do Pythagorean theorem if we went straight across, we would do 6 squared plus 17 squared plus 17 squared and square root it. So the distance that she's looking at would be 18.2 something. So 18.0277. And if she went that distance, the amount of time that it would take would be pure rowing. So we would multiply that by 2. Sorry, we would do 17. Hold on a minute. So I'm just messing that up. I can't do an 18 point something. Because I would be shooting for my X value. It's all based on my X value. So my X value would be 17. And so if I did that, her distance would be that, but we would be plugging it into this equation. So we would be 17 squared plus the 36 and Pythagorean theorem, that thing, divided by 2 is what we would be doing. So I finish my formula. So we would take 17 squared plus 36 squared plus 36, which is what we have here. And then we would divide it by 2, and that would give us our time that it takes, which is 9.019. We'll call it. Sorry, 3, 4. And so if she went straight across, it would take her 8.6-ish hours. If she rode the whole thing, it would take her 9 hours. But if she did a combination of the two exactly at that distance down the coast, that would be her best time. If she went a little bit shallower or a little bit further, those times would be a little bit bigger than that.